Another connection between the galaxy's scale and the solar system involves radiation. The Milky Way is not a quiet place in energetic terms. Supernovae, the explosive deaths of massive stars, occur regularly somewhere in the galaxy. These events release enormous amounts of energy and high-energy particles into space. Most of the time, these explosions happen far enough away that their effects on the solar system are minimal. But over geological timescales, there may have been supernovae close enough to Earth to influence the planet's environment, potentially affecting its atmosphere or climate. If the Milky Way structure includes extended regions of star formation that were previously underappreciated, it could influence how astronomers model the distribution and frequency of such energetic events. The solar system's position in the galaxy, about 26,000 light-years from the center, places it in a relatively calm region compared to the crowded active core. But as the understanding of the galaxy's scale and structure becomes more detailed, the context of that calm can be refined. For example, the solar system's distance from the galactic center and its position relative to spiral arms can be considered alongside the distribution of halo stars, gas clouds, and dark matter structures. This broader context helps astronomers evaluate how typical or atypical our galactic environment might be. There is also the question of chemical history. The elements that make up the Earth, the Sun, and everything living on this planet were forged in earlier generations of stars. When those stars ended their lives, they returned those elements to the interstellar medium, where they became part of new stars and planetary systems. The distribution of these elements across the galaxy is not uniform. Regions that have experienced more star formation and more supernovae tend to be richer in heavier elements. Regions that are more isolated or have had fewer such events tend to be more chemically primitive. As the Milky Way structure is mapped in greater detail, including its extended halo and streams of stars from past mergers, it becomes possible to trace how different parts of the galaxy have contributed to the overall chemical makeup of the interstellar medium. The solar system formed from a cloud of gas and dust that had been enriched by previous generations of stars. Understanding where that cloud came from and what kind of galactic environment it was embedded in is part of understanding how the conditions for planets and life arose. If the galaxy's halo contains remnants of smaller galaxies with different chemical histories, and if material from those systems has mixed into the disk over time, then the solar system's ingredients may reflect a broader galactic heritage than once assumed. Another way to think about the new scale of the galaxy is in terms of motion through time. The Milky Way is not static. It is moving through the local group of galaxies, and its own internal structure is evolving. Over billions of years, the positions of spiral arms shift, satellite galaxies merge, and streams of stars are stretched and dispersed. The solar system's path is embedded in this larger flow. If the galaxy's halo is more extended and structured, then the gravitational landscape through which the solar system moves is also more complex. The Sun's orbit is influenced not just by the mass of the disk and bulge, but by the distribution of dark matter and the presence of massive structures in the halo. These influences are small on human timescales, but over millions and billions of years, they shape the overall trajectory of the solar system. This long-term perspective can make the solar system feel less like an isolated bubble and more like a traveller in a vast interconnected system. There is also a shift in how home can be understood. For much of modern astronomy, the solar system's address was given in simple terms: a planet orbiting a star located in a spiral arm of the Milky Way, one of many galaxies in the universe. As the picture of the Milky Way grows more detailed and more expansive, that address becomes more layered. The solar system is part of the thin disk. The thin disk is embedded in a thick disk. Both are surrounded by a halo of ancient stars and dark matter. That halo overlaps with the halos of neighbouring galaxies. Those galaxies are part of a group. That group is part of a larger filament of galaxies. Each layer adds context to the one below it. This does not change the practical reality of life on Earth. The sun still rises and sets. The seasons still change. The night sky still looks much the same as it did before these new observations, but it changes the background story. When you look up at the stars, you're not just looking at a flat pattern of points. You're looking into a deep layered structure that extends far beyond what the eye can see, and that includes regions and populations of stars that were, until recently, largely unknown. there is also a subtle effect on how astronomers think about the search for life elsewhere. The habitability of a planetary system can be influenced by its galactic environment. Regions with very high rates of star formation and supernova activity might be more hazardous for life due to increased radiation and gravitational disturbances. Regions that are too isolated might lack the heavier elements needed to form rocky planets in the first place. By refining the map of the Milky Way's structure and scale, scientists can better understand where different kinds of environments exist within the galaxy. The solar system's position, in a relatively quiet part of the disk with a moderate abundance of heavy elements, appears to be a favourable one for the development of complex life. As the galaxy's extended halo and streams are studied in more detail, it becomes possible to compare our local environment to those of stars that formed in very different parts of the galaxy, or even in different galaxies that were later absorbed. This comparative approach can help identify what aspects of the solar system's history are typical and what might be more unusual. There is also a connection to the future. The Milky Way and Andromeda are on a slow collision course. In about 4 billion years, they will begin to merge, eventually forming a single, larger galaxy. In that distant future, the structure and scale of the Milky Way will change dramatically. The disk will be disrupted, the halo will be reshaped, streams of stars will be mixed and scattered. The solar system will still be there, orbiting within this evolving structure, although its path and environment will be altered. Understanding the Milky Way's current scale and structure helps set the stage for understanding how this future transformation might unfold. It also places the solar system's present situation in a much longer narrative, one that stretches from the early assembly of the galaxy to its eventual merger with a neighbour. On a more immediate human level, there is something quietly grounding about connecting the small and the large in this way. The objects in the solar system, the Earth, the Moon, the planets, the distant comets, all feel tangible. They can be seen, touched indirectly, or visited by spacecraft. The galaxy, by contrast, feels abstract and remote. By understanding how the two are linked, how the solar system moves within the Milky Way's extended structure and responds to its gravitational and energetic environment, that sense of separation softens. The solar system becomes part of a continuous system rather than a small isolated island. This perspective can also influence how astronomers interpret the past of the solar system. There are clues in the geological record on Earth, in the distribution of craters on the Moon, and in the composition of meteorites that hint at changes in the rate of impacts or the influx of material over time. Some of these changes may be connected to the solar system's movement through different regions of the galaxy, such as passing through denser clouds of gas or near spiral arms. As the Milky Way structure is mapped in greater detail, it becomes possible to model these journeys more accurately, linking events in the solar system's history to specific galactic environments. This does not mean that every major event on Earth can be traced back to a galactic cause. Many things are driven by local processes, but it does mean that the broader galactic context is part of the story. Another aspect to consider is how the new sense of scale affects our emotional relationship to the cosmos. There is a long tradition in science and philosophy of reflecting on humanity's place in the universe. Discoveries that expand the known size of the cosmos often come with a sense of humility. When the Earth was found to orbit the Sun, and the Sun was found to be one star among many, and the Milky Way was found to be one galaxy among billions, each step reduced our apparent centrality. The realization that even our own galaxy is more extended and more complex than we thought continues that trend. It suggests that our home is larger, more layered, and more interconnected than we previously imagined. This does not make human experiences smaller in a meaningful sense. It simply places them within a broader framework. From the perspective of the Milky Way's extended halo, the solar system is a tiny moving point. From the perspective of a human life, the solar system is a stable, enduring environment. Both perspectives are true at the same time. As astronomers continue to refine their understanding of the galaxy's scale, the relationship between the solar system and the Milky Way will likely become even more detailed. New surveys may reveal additional structures in the halo, new streams of stars, or subtle variations in the dark matter distribution that influence the Sun's long-term path. Each of these discoveries will add another layer to the story of how the solar system fits into the galaxy. In the end, what the new scale of the Milky Way means for our solar system is not a dramatic change in daily reality. The planets will not shift in their orbits because a telescope has revealed more distant stars. But it does change the narrative context. The solar system becomes part of a larger, more extended and more intricate system than the one that existed in our mental maps before. It becomes a traveller in a vast layered structure that stretches far beyond the bright band of the Milky Way we see in the night sky. Maps are usually made with the comforting assumption that the place being mapped will stay still long enough for the ink to dry. Roads don't slide across the page. Rivers may bend over centuries, but not while you're drawing them. Mountains stay put, at least on human timescales. A map, once finished, can sit on a wall and remain useful for years, even decades, without changing very much. A galactic map does not have that luxury. The Milky Way is not a fixed landscape. It is a moving system, a vast collection of stars, gas, dust and dark matter, all orbiting, drifting and evolving at different speeds and on different paths. Trying to draw a map of something like that is less like sketching a city, and more like trying to chart the shape of a slow, shifting cloud. At the heart of this challenge is the relationship between time and distance. In everyday life, distance is something you can cross. You walk across a room, you drive across a town. Time passes, but the place itself doesn't fundamentally change while you're moving through it. In astronomy, distance is also time. Light takes time to travel. The farther away something is, the farther back in time you're seeing it. This simple fact turns every observation of the Milky Way into a kind of time travel. When you look at a star that is 1,000 light-years away, you're seeing it as it was 1,000 years ago. When you observe the center of the galaxy, 26,000 light-years away, you're seeing a version of that region that existed when human civilization was just beginning to develop agriculture. When astronomers try to assemble a map of the galaxy, they are not working with a single snapshot. They are piecing together views from many different moments in the past. That alone would be complicated enough, but the galaxy itself is changing during those times. Stars move along their orbits, gas clouds collapse and disperse, spiral patterns shift, satellite galaxies pass by and leave behind streams of stars. The structure being mapped is in motion even as its light is on its way to us. So a galactic map is not a picture of the Milky Way at one moment. It is a collage of moments, stitched together into something that approximates the present. This creates a subtle but important tension. On the one hand, the galaxy evolves slowly. Over the span of a human lifetime, or even over the few decades that modern astronomy has been active, the large-scale structure of the Milky Way does not change dramatically. The spiral pattern remains, the disk and halo remain. The overall distribution of stars looks much the same. On the other hand, when you're working with timescales of tens of thousands or hundreds of thousands of years, small motions can add up. A star in the disk can move a significant fraction of its orbit in that time. A stream in the halo can stretch and thin. Gas clouds can form new stars and be reshaped by their radiation. So when light from different parts of the galaxy reaches Earth, it is carrying information from different stages of this ongoing process. Astronomers account for this by treating the galaxy as if it were, for the most part, in a steady state. This is a reasonable approximation for many purposes. The Milky Way is not undergoing a dramatic, sudden transformation at the moment. It is changing gradually. But the approximation has limits. As observations become more precise and reach farther into the halo and the outskirts of the galaxy, those limits start to matter more. Subtle differences in timing and motion can affect how features are interpreted. Consider something as seemingly simple as a star stream in the halo. A stream is made up of stars that once belonged to a smaller galaxy, or star cluster, that was pulled apart by the Milky Way's gravity. Those stars now follow similar orbits, forming a long, thin structure that wraps around the galaxy. When we observe a stream, we are seeing different parts of it at different times. The stars closer to us are being seen more recently. The stars farther away are being seen further back in time. Because the stream is moving and stretching, the shape we observe is not exactly the shape it has at any single moment. It is a time-smeared version of the structure. This does not make the observation useless. It just means that interpreting it requires careful modelling of how the stream moves and evolves over time. The same is true for the disk. When astronomers map the spiral arms, they are tracing patterns in the distribution of gas and young stars. Those patterns are dynamic. They shift and change as material moves through the galaxy. The arms we see in one part of the galaxy are not necessarily in exactly the same configuration as the arms in another part, because we're seeing them at slightly different times. This can lead to apparent irregularities or mismatches in the map that are not necessarily real features of the galaxy, but artifacts of the time delay in the observations. Then there is the problem of scale. The Milky Way is so large that no single method can map it completely. Astronomers use a combination of techniques, each of which works best in a particular range of distances. Parallax measurements provide very precise distances for nearby stars, out to a few thousand light-years. Beyond that, standard candles and other methods take over, with larger uncertainties. For the outer halo and distant satellite galaxies, distances may be estimated based on models of motion and gravity rather than direct measurement. Each of these layers of the map has its own resolution and its own error bars. When they're combined into a single picture, those differences can create distortions. It is a bit like stitching together photographs taken with different cameras and lenses. Some parts of the image will be sharp and detailed, others will be grainy or slightly blurred. The transitions between them can be tricky to handle. Astronomers work hard to calibrate these different data sets so that they align as well as possible. But there is always some level of uncertainty in how the pieces fit together. Another challenge comes from the fact that the Milky Way is not evenly populated. In some regions, stars are packed closely together. In others, they are sparse. The density can change dramatically over relatively small distances, especially in the halo and the outer disk. This unevenness means that some parts of the galaxy are easier to map than others. In a dense star field, there are many data points to work with. In a sparse region, a single star can carry a lot of weight in defining the structure. If that star is misclassified or its distance is measured incorrectly, it can shift the apparent boundary of the galaxy in that direction. This is one reason why the discovery of faint distant stars with instruments like James Webb can have an outsized impact on models of the galaxy's scale. Each new reliable detection in the outskirts adds a point to the map where previously there might have been nothing. Over time, these points can change the perceived shape and extent of the Milky Way. There is also the issue of perspective. Because we are inside the galaxy, we see it from a very specific vantage point. Our view is heavily influenced by our position in the disk, about 26,000 light-years from the center. This internal perspective means that some features are always going to be easier to see than others. For example, the far side of the galaxy is harder to study because its light has to pass through the dense, dusty regions near the center to reach us. Even in the infrared, that path is not completely clear. As a result, the near side of the disk is often better mapped than the far side. This can create asymmetries in galactic maps that reflect observational bias, rather than true differences in structure. Astronomers try to correct for this by using models and by comparing observations in different directions, but the bias can never be completely eliminated. Then there is the problem of distinguishing between what belongs to the Milky Way and what does not. When you look out toward the edge of the galaxy, you're also looking beyond it. Distant galaxies, quasars, and other extragalactic objects appear in the same field of view as faint halo stars. Separating these populations is not always straightforward, especially when dealing with very faint sources. Infrared observations help, as do measurements of motion. Stars in the Milky Way will show proper motion across the sky over time, while distant galaxies will not. But these measurements require long-term data and high precision. Until that information is available, some sources may be misidentified, affecting the map. The problem of galactic maps is not just technical, it is also conceptual. When people think of a map, they often imagine something with clear boundaries and labels. This city ends here, that river starts there, this country has a border at this line. The Milky Way does not have borders in that sense. Its density of stars and gas fades gradually. Its dark matter halo extends far beyond its visible components. Its gravitational influence overlaps with that of neighboring galaxies. So any attempt to draw a line around the galaxy is, to some extent, an arbitrary choice. Astronomers may define the edge of the galaxy based on where the stellar density drops below a certain level, or where the gravitational influence of the Milky Way becomes weaker than that of Andromeda, or where the dark matter halo is thought to taper off. Each of these definitions produces a different map. This means that when new observations suggest the galaxy is larger than previously thought, what is often changing is not the physical galaxy itself, but the definition of which part of it is being emphasized. If you start including more of the halo, or if you refine your estimate of the dark matter distribution, the map grows. This flexibility can be confusing, especially outside of scientific contexts, where people may be looking for a single, definitive answer to the question, how big is the Milky Way? In reality, there are several answers, each corresponding to a different component of the galaxy. The disk has one size, the stellar halo has another, the gas halo has another, the dark matter halo has yet another. A galactic map that tries to include all of these components has to be multi-layered, more like a set of transparent sheets than a single flat image. Another complication comes from the tools used to make these maps. Modern galactic cartography relies heavily on large surveys that collect data on millions or billions of stars. Missions like Gaia provide incredibly detailed information about the positions and motions of stars, but they are optimized for certain types of observations. Gaia, for example, works primarily in visible light and is most sensitive to stars in the disk and nearby halo. It struggles in regions of very high dust density and in detecting very faint, cool stars. James Webb, on the other hand, excels in the infrared and can see into dusty regions and detect faint objects, but it does not survey the entire sky. Its field of view is relatively small, and its observations are targeted rather than comprehensive. So each instrument provides a different piece of the map, and those pieces have to be combined. This combination process is complex. It involves matching stars across different catalogues, reconciling different distance scales, and accounting for different selection effects. Selection effects are biases introduced by the way a survey is conducted. For example, a survey that only detects stars brighter than a certain limit will naturally miss fainter stars, which can skew the apparent distribution. Correcting for these effects requires careful statistical modelling and assumptions about the underlying population. As the galaxy's map extends farther into the halo and the outskirts, these corrections become more important, because the stars being studied are often right at the limits of detectability. Another layer of complexity comes from the fact that not all parts of the galaxy are equally well studied. Some regions have been the focus of multiple surveys and detailed follow-up observations. Others have only been observed in passing. This uneven coverage can create gaps in the map, areas where the structure is inferred rather than directly observed. Webb's targeted observations can help fill in some of these gaps, especially in dusty or faint regions. But because its time is limited and its field of view is small, it cannot by itself create a complete, uniform map of the galaxy. Instead, it adds depth and detail to specific areas, which then have to be integrated into the broader picture. This process of integration is ongoing. Astronomers constantly update their models of the Milky Way as new data comes in. Distances are revised. Structures are reinterpreted. Features that were once thought to be separate may turn out to be connected, or vice versa. This means that a galactic map is never truly finished. It is more like a living document, a representation that evolves as our tools and understanding improve. There is something quietly fitting about this. The Milky Way itself is not finished. It is still forming stars. It is still interacting with its neighbours. It is still growing and changing. A map that captures it perfectly, once and for all, would almost feel out of place. From a more reflective point of view, the problem of galactic maps highlights a broader theme in science. We often talk about knowing something, but that knowledge is always provisional. It is based on the best available evidence and the best available models, and it is always open to revision. When new observations extend the known size of the Milky Way, they are not overturning everything that came before. They are refining it, adding layers and nuance. This can be seen as a kind of dialogue between the universe and the people studying it. The universe presents itself in the form of light, motion, and structure. Scientists respond by building instruments, creating models, and drawing maps. Those maps, in turn, guide the next round of questions and observations. Time and distance play a role on both sides of this dialogue. The light that reaches us carries information from the past. The maps we draw influence the future of research. In the context of the Milky Way's scale, this dialogue is particularly vivid. Each new detection of a distant star, each refined measurement of a halo stream, each improved model of the dark matter distribution adds a small piece to the map. Over time, these pieces accumulate, and the outline of the galaxy grows more extended, more complex and more detailed. But the process never quite reaches a point where it can stop and declare itself complete. There will always be fainter stars, more distant structures, and subtler motions to discover. In that sense, a galactic map is less like a finished product and more like a path. It is a way of organizing what we currently know, while leaving room for what we have yet to learn. As James Webb and other observatories continue to add new information to this evolving picture, the Milky Way's map will continue to change. Not in sudden, dramatic shifts, but in small, steady adjustments that gradually reshape how the galaxy is understood. Across the vast range of galaxies scattered through the observable universe, the Milky Way has always occupied an interesting middle ground. It has never been considered a giant among giants, like the enormous elliptical galaxies that dominate the centers of galaxy clusters. At the same time, it has never been seen as a small or fragile system, like the faint dwarf galaxies that orbit larger hosts or drift quietly through intergalactic space. It has long been described as a fairly typical spiral galaxy, substantial, well-structured, and comfortably average in many respects. As new observations refine the Milky Way's true scale and reveal a more extended, layered, and complex structure, that sense of typical begins to shift in subtle ways. The first step in comparing our galaxy to others is deciding what features to compare. Galaxies come in a wide range of shapes and sizes. Some are spirals, with disks and arms like the Milky Way. Others are ellipticals, smooth and rounded, often filled with older stars and little gas. Still others are irregular, lacking a clear structure and shaped by interactions and internal turbulence. Even within the category of spiral galaxies, there is enormous variety. Some have tightly wound arms and bright central bulges. Others have loose, sweeping arms and relatively small cores. Some are rich in gas and actively forming stars. Others are more sedate, having used up much of their star-forming material. For a long time, the Milky Way was thought to sit comfortably among the larger spiral galaxies, but not at the extreme end of the scale. Its bright disk, about 100,000 light-years across, placed it in a similar category to galaxies like Andromeda and Triangulum, though Andromeda was generally considered slightly larger and more massive. As the picture of the Milky Way's halo and dark matter distribution becomes more detailed, that comparison becomes more nuanced. One of the most important measures of a galaxy's size is not just how far its stars extend, but how much mass it contains. Most of a galaxy's mass is not in its stars or gas, but in its dark matter, halo. This halo shapes the orbits of stars and satellite galaxies and determines how strongly the galaxy interacts with its neighbours. Estimates of the Milky Way's total mass have varied over the years, partly because the halo is difficult to study. The farther out you go, the fewer stars and satellites there are to use as tracers of the gravitational field. As new data, including observations of faint halo stars and the motions of distant satellite galaxies, improve these estimates, the Milky Way appears to be more massive than some earlier models suggested. This has implications for how it compares to other galaxies. If the Milky Way's dark matter halo is larger and more massive, then its gravitational reach is greater. This can influence how it interacts with nearby systems, how it captures or disrupts satellite galaxies, and how it fits into the larger structure of the local group. In terms of mass, the Milky Way and Andromeda are now thought to be more comparable than previously believed, though there is still uncertainty about which one is truly the heavier of the two. This near parity between the two largest members of the local group paints a picture of a future merger between roughly equal partners, rather than a small galaxy being absorbed by a much larger one. That future event, sometimes called Milkomeda or Milkdromeda, will reshape both galaxies, blending their stars, gas, and dark matter into a single, larger system. Looking outward, beyond the local group, astronomers study thousands of other galaxies to see where the Milky Way fits into the broader population. Large surveys of the sky have revealed that spiral galaxies of similar mass and brightness to the Milky Way are fairly common. They often reside in small groups rather than in the dense cores of galaxy clusters. This environment matters. Galaxies and clusters are subjected to strong gravitational interactions and hot, dense gas that can strip away their own gas and shut down star formation. They often evolve into elliptical or lenticular shapes. Galaxies in smaller groups, like the Milky Way, tend to retain their gas for longer and continue forming stars over extended periods. This makes the Milky Way's continued star formation, moderate spiral structure, and extended halo consistent with what astronomers see in other group environments. What has become more interesting is the level of structure and substructure in the Milky Way's halo. As observations reveal more streams and remnants of past mergers, the Milky Way begins to look like a particularly active collector of smaller galaxies. This is not unique. Many large galaxies show evidence of similar processes. In deep images of nearby galaxies, astronomers can see faint tidal streams and shells of stars around their outskirts, signs of past interactions. These features are often extremely faint and require long exposures to detect. The Milky Way, being so close, allows these features to be studied in much greater detail. When Webb and other instruments help trace the halo structure, they are providing a level of insight into galaxy growth that is hard to achieve for more distant systems. This has a feedback effect on how other galaxies are interpreted. If the Milky Way's halo is more extended and more structured than previously thought, it suggests that other spiral galaxies of similar mass may also have complex, far-reaching halos that are simply difficult to detect at great distances. In that sense, the Milky Way becomes a kind of reference point, a nearby example that can inform models of galaxy formation and evolution more broadly. Another area of comparison involves the distribution of stars within the disk. The Milky Way's disk appears to be fairly typical in terms of its thickness and star formation rate compared to other spiral galaxies of similar mass. It is not a starburst galaxy, where stars are forming at an exceptionally high rate. It is also not a quiescent galaxy, where star formation has largely ceased. It sits in a middle range, forming a few new stars per year, a pace that seems to be common among similar systems. What has changed with improved mapping is the sense of how far the disk and thick disk extend. If the Milky Way's stellar populations reach farther out than once thought, it may place the galaxy toward the larger end of the scale for disk galaxies. This does not necessarily make it exceptional, but it does suggest that its structure is more expansive than the simple, tidy picture often presented. There is also the matter of chemical composition. By comparing the chemical makeup of stars in the Milky Way to those in other galaxies, astronomers can learn about the history of star formation and enrichment. The Milky Way shows a range of metallicities, with stars near the center and in the thin disk generally richer in heavy elements, and stars in the halo and thick disk often more primitive. This pattern is seen in many other spiral galaxies as well. What makes the Milky Way especially valuable is the level of detail that can be achieved, because we can study individual stars in our own galaxy, rather than just the combined light of billions of stars. We can trace chemical gradients and variations with much higher resolution. This detailed view helps calibrate methods used to study more distant galaxies, where such fine-grained analysis is not possible. In terms of overall appearance, if an observer could somehow view the Milky Way from outside, it would likely resemble many of the spiral galaxies seen in deep field images. It would have a bright barred center, a set of spiral arms, and a faint extended halo. What would be harder to see, without long sensitive exposures, are the subtle features in the halo, the streams, shells, and faint stellar populations that hint at the galaxy's complex history. These features are now known to be common in large galaxies, but the Milky Way's proximity allows them to be studied in much greater detail than in most other systems. Another point of comparison is the galaxy's role within its local environment. The Milky Way and Andromeda dominate the local group, along with a few dozen smaller galaxies. This is a relatively small and loose association compared to massive clusters like the Virgo cluster, which contains thousands of galaxies bound together by gravity. In clusters, galaxies experience frequent interactions, high-speed encounters, and the influence of hot, diffuse gas that fills the space between them. In the local group, interactions are less violent and more gradual. This environment allows galaxies like the Milky Way to maintain their disks and continue forming stars over long periods. The extended halo and complex structure of the Milky Way can be seen, in part, as a product of this environment. It has had time to grow through mergers with smaller galaxies without being subjected to the disruptive forces present in dense clusters. When astronomers compare the Milky Way to spiral galaxies in different environments, they often find that group galaxies tend to have richer halos and more pronounced signs of past mergers than isolated galaxies. This fits with the idea that small groups provide a steady supply of satellite galaxies that can be absorbed over time. Looking beyond the local universe, surveys of distant galaxies show that galaxy formation and evolution have changed over cosmic time. In the early universe, galaxies were generally smaller, more irregular, and more actively forming stars. Mergers were more common, and structures were less settled. As the universe aged, galaxies grew, disks formed, and star formation rates declined. The Milky Way's extended halo and layered structure can be seen as the outcome of this long process. It is a mature galaxy, one that has had billions of years to assemble its mass, form its disk, and accumulate a complex halo of stars and dark matter. In this context, the Milky Way serves as an example of what a large spiral galaxy can look like in the later stages of cosmic history. Comparisons with distant galaxies allow astronomers to place our own galaxy on a kind of evolutionary timeline. By looking at galaxies at different distances, and therefore at different points in the past, scientists can infer how systems like the Milky Way might have looked when they were younger. This, in turn, helps interpret the structures seen in the Milky Way's halo as relics of earlier phases of growth. Another interesting comparison involves the presence of satellite galaxies. The Milky Way has dozens of known dwarf companions, some bright and well-studied, others faint and difficult to detect. Recent surveys have continued to discover new, ultra-faint dwarf galaxies in its vicinity. This population of satellites is an important test of cosmological models, particularly those related to dark matter. Some models predict that large galaxies should be surrounded by many small dark matter clumps, some of which host stars and become visible as dwarf galaxies. The number and distribution of these satellites around the Milky Way are compared to similar systems around other galaxies to test these predictions. As the Milky Way's halo is mapped in greater detail, including faint stars and streams, it becomes possible to better understand how these satellites are distributed and how they have interacted with the main galaxy over time. This again feeds back into comparisons with other galaxies. If the Milky Way's halo is particularly rich in substructure, it may suggest a more active merger history than average. Alternatively, it may indicate that similar structures exist around other galaxies but are simply harder to detect at greater distances. In that sense, the Milky Way may not be unusual in its complexity, but it may be unusually well observed. There is also the question of scale in terms of influence. Some galaxies, particularly massive ellipticals in clusters, exert strong gravitational effects on their surroundings, shaping the motion of many nearby galaxies. The Milky Way's influence is more modest, limited largely to the local group. But within that group it plays a significant role. Its extended dark matter halo helps define the gravitational landscape that smaller galaxies move through. As estimates of the halo's size and mass are refined, the Milky Way's role within the local group can be better understood. This includes how it and Andromeda together shape the motions of more distant group members. From a broader perspective, comparing the Milky Way to other galaxies is not just about ranking it on a scale of size or mass. It is about understanding it as one example in a diverse population of systems, each shaped by its own history and environment. The realization that the Milky Way is wider, deeper, and more layered than once thought does not necessarily make it exceptional. It makes it more clearly part of a general pattern, where large galaxies grow through mergers, develop complex halos, and exist within overlapping gravitational environments. What changes is the level of detail in which this pattern can be studied. Because we are inside the Milky Way, we can observe it star by star, stream by stream, and cloud by cloud. This provides a kind of ground truth for models of galaxy formation that are applied to the distant universe. In that sense, the Milky Way is both an ordinary spiral galaxy and a special one. It is ordinary in its basic type and scale. It is special in its proximity and the level of detail it offers. As the picture of its true scale becomes more refined, its role as a reference point in the study of galaxies becomes even more important. Astronomers can use what they learn about the Milky Way's extended halo, its merger history, and its dark matter distribution to interpret observations of galaxies that are too far away to be studied in such detail. This creates a kind of bridge between the local and the cosmic. The Milky Way becomes a lens through which the broader population of galaxies can be better understood, and at the same time, comparisons with other galaxies help put the Milky Way in context, preventing it from being seen as either uniquely special or entirely unremarkable. It occupies a place in a wide spectrum of galactic forms, shaped by its own particular history, but governed by the same physical processes that operate across the universe. As new observations continue to expand the known reach of our galaxy, this interplay between the local and the distant is likely to deepen. Each refinement in our understanding of the Milky Way feeds into models of how galaxies form, grow, and interact. Each new comparison with other systems helps clarify what is typical and what is distinctive. In that ongoing exchange, the Milky Way's newly appreciated scale becomes not just a fact about our own cosmic home, but a piece of a much larger story about how structure emerges in the universe, one galaxy at a time. Beyond the reach of even the most advanced telescopes, there remains a layer of the Milky Way that is defined not by what is visible, but by what is inferred. This unseen side of the galaxy is not a small or trivial addition to the picture. In many ways, it makes up most of what the galaxy actually is. When people imagine the Milky Way, they tend to think of stars, bright points of light, glowing clouds of gas, dark lanes of dust. These are the features that shape the familiar image of a spiral galaxy. But all of these visible components together account for only a fraction of the galaxy's total mass. The majority of the Milky Way is invisible. This invisible component is known as dark matter, and it forms a vast halo that surrounds and permeates the galaxy. It does not emit light, it does not absorb light, it does not reflect light. Its presence is detected only through its gravitational effects on the things we can see. Stars orbit the center of the galaxy faster than they should if only the visible matter were present. Satellite galaxies move along paths that suggest they are being held by a much stronger gravitational field than the stars and gas alone could provide. Streams of stars in the halo curve and stretch in ways that reveal the shape of an unseen mass distribution. All of these clues point to a halo of dark matter that is far larger and more massive than the visible galaxy. James Webb cannot see this halo directly. No telescope can, at least not in the sense of capturing an image. But by revealing faint stars in the outskirts of the galaxy and helping trace their motions, Webb contributes to the indirect mapping of this invisible structure. Even so, the dark matter halo remains in many respects a shadow. Astronomers can estimate its size, its mass, and its general shape. But these estimates come with wide margins of uncertainty. Different models can fit the same data. Different assumptions about the nature of dark matter can lead to different conclusions about how it is distributed. Some models suggest that the halo is roughly spherical. Others indicate that it may be stretched or flattened, perhaps aligned with the disk or tilted at an angle. There are also questions about how smooth the halo is. According to many theories, dark matter should clump on small scales, forming a network of subhalos, smaller concentrations of dark matter within the larger halo. Some of these subhalos may host visible dwarf galaxies. Others may be completely dark, containing little or no stars at all. If these dark substructures exist, they would influence the motion of stars and gas in subtle ways, creating small distortions in streams and orbits that can be detected with careful measurement. So far, evidence for such subhalos is indirect and incomplete. Some stellar streams show signs of having been perturbed by something unseen, possibly a dark matter clump passing nearby, but these cases are rare and difficult to interpret. This means that a large part of the Milky Way's true structure is still known only through hints and models, not through direct observation. There is also the question of the galaxy's outermost regions. As faint stars are discovered farther and farther from the center, the apparent boundary of the Milky Way continues to move outward. But there will always be a point where stars become so sparse that it is hard to tell whether a given star truly belongs to the galaxy or is part of the intergalactic background. At these extreme distances, the gravitational pull of the Milky Way weakens, and the influence of neighboring galaxies, especially Andromeda, becomes more significant. This creates a kind of transition zone, where the concept of inside and outside the galaxy loses its clarity. Webb can help push the detection of stars into these regions, but there are practical limits. Even with its sensitivity, there will be stars that are simply too faint or too isolated to be detected. Beyond them lies a region that may still be gravitationally connected to the Milky Way through dark matter, but that contains little or no visible matter at all. This region is, by definition, invisible in the traditional sense. Another layer of what cannot be seen lies in the early history of the galaxy. The Milky Way formed more than 13 billion years ago in the aftermath of the Big Bang, when the universe was much younger and denser. The earliest stages of its formation involved the collapse of gas and dark matter into the first small structures, which then merged and grew into larger systems. None of the direct evidence from that era remains in a form that can be observed easily. The oldest stars in the Milky Way, found mainly in the halo, carry chemical signatures of those early times. Their compositions reveal how much heavy material was present when they formed, which in turn reflects how many generations of stars had lived and died before them. But these stars are only indirect messengers. They do not show us the galaxy as it was in its infancy. They provide clues that must be interpreted through models of stellar evolution and chemical enrichment. In this sense, a large part of the Milky Way's past is also invisible, hidden not by distance or dust, but by time. There is also the matter of the interstellar medium. Between the stars lies a complex mixture of gas in different phases, from cold, dense molecular clouds to hot, diffuse plasma. Some of this gas can be detected through radio waves, some through infrared emission, some through absorption lines in the spectra of background sources. But there are regions, especially in the hot diffuse halo, where the gas is so thin and so spread out that it is difficult to observe directly. This hot gas is thought to form a vast envelope around the galaxy, extending far beyond the visible disk. It plays an important role in the galaxy's evolution, acting as a reservoir of material that can cool and fall back into the disk, as well as a sink for energy and matter ejected by supernovae and stellar winds. Despite its importance, much of this gas remains poorly mapped. Its density, temperature and distribution are known only in broad terms, inferred from a small number of observations and models. This means that another major component of the Milky Way structure exists in a kind of observational twilight, neither fully visible nor entirely theoretical. Then there are the smallest scales. Even within regions that are well observed, there are details that remain beyond reach. In star-forming clouds, for example, the processes that determine how individual stars and planetary systems form happen on scales that are difficult to resolve, even with powerful telescopes. Webb can see into these clouds and reveal structures that were previously hidden, but there will always be finer details, smaller motions, and more subtle interactions that lie below the threshold of detection. This means that the Milky Way, at every level from its vast dark matter halo down to the formation of individual stars, contains layers of complexity that are only partially accessible. Another category of what cannot be seen involves phenomena that do not produce light in the usual sense. Gravitational waves, for example, ripple through space-time when massive objects like black holes and neutron stars merge. These waves pass through the Milky Way and through Earth, carrying information about distant and violent events. They are not detected by telescopes, but by specialized instruments that measure tiny distortions in space itself. In this way, there is a whole layer of galactic activity that exists outside the realm of electromagnetic observation. Similarly, neutrinos, nearly massless particles produced in nuclear reactions and stellar explosions, stream through the galaxy and through our bodies without leaving much trace. They carry information about processes deep inside stars and supernovae that cannot be seen directly. These forms of messengers add to the sense that the galaxy is more than what appears in images, even in the most detailed ones. They suggest that there are aspects of the Milky Way that are accessible only through entirely different kinds of observation, and that many of those methods are still in their early stages. There is also the possibility that some parts of the galaxy are hidden, not just from our instruments, but from our current understanding. Dark matter itself is an example of this. We know it exists because of its gravitational effects, but we do not know what it is made of. There are many theories, involving exotic particles and new physics, but no definitive answer. If the nature of dark matter turns out to be very different from what is currently assumed, it could change how astronomers interpret the structure and scale of the Milky Way. For example, if dark matter interacts with itself, or with ordinary matter in subtle ways, it could affect how the halo is shaped and how it evolves over time. These possibilities add another layer of uncertainty to the unseen side of the galaxy. There is also the question of whether there are entire populations of objects that we have not yet recognized. In the past, astronomers were surprised to discover things like pulsars, quasars, and gamma-ray bursts, phenomena that were not predicted by earlier theories. It is possible that there are classes of objects in the Milky Way that have not yet been identified, either because they are rare, faint, or emit primarily in ways that have not been thoroughly explored. Webb expands the range of what can be seen in the infrared, but it does not cover every possible window. There are still regions of the electromagnetic spectrum that are difficult to observe from space or from the ground, and there are observational techniques that are still being developed. This means that the picture of the Milky Way is likely to continue changing as new tools and methods come online. Another aspect of what cannot be seen is the future. The Milky Way structure will change over time. Stars will move, new stars will form, old stars will die, satellite galaxies will merge. The dark matter halo will evolve as well, influenced by the motions of the galaxy and its neighbours. We can model these processes and make predictions, but we cannot observe them directly, at least not on the timescales that matter for galactic evolution. This means that the galaxy we map today is only one moment in a long sequence of forms. There are past versions of the Milky Way that are lost to time, and future versions that exist only in simulations. In this sense, a large part of the galaxy is always invisible, either because it has not yet happened or because it has already passed. There is also a more philosophical layer to this idea of unseen structure. Every map, every model, every image is a representation, not the thing itself. The Milky Way as it exists in reality is a complex multi-dimensional system of matter, energy, and space-time. The Milky Way as it exists in our minds is a simplified version of that system, shaped by the limits of our senses, our instruments, and our theories. What we cannot see, in this sense, includes not just physical components like dark matter and faint gas, but also aspects of the galaxy that do not fit neatly into our current conceptual frameworks. As science advances, some of these invisible aspects become visible, either literally through new kinds of observation or figuratively through new ideas that allow old data to be interpreted in new ways. This process has happened many times in the history of astronomy. Planets were once seen as wandering stars. Galaxies were once thought to be clouds within the Milky Way. Dark matter was once an unexpected anomaly in measurements of galactic rotation. Each shift expanded the known universe and redefined what was considered visible. The Milky Way today is already far more detailed and more complex than it was in the imagination of astronomers a century ago, and yet, by most measures, a large part of it remains unseen. This is not a failure of observation so much as a reflection of scale. When a system spans hundreds of thousands of light years and includes components that do not interact with light at all, it is inevitable that some of it will lie beyond direct view. What changes over time is not the existence of this unseen side, but how much of it can be inferred, modelled, and understood. As instruments like James Webb continue to refine the visible picture, they also sharpen the contrast with what remains invisible. Each new discovery highlights not only what has been revealed, but what still lies beyond the edge of observation. This tension between the seen and the unseen is part of what drives the ongoing exploration of the galaxy. It keeps the map unfinished, the questions open, and the sense of scale flexible rather than fixed. In that way, the Milky Way remains, even in the age of advanced telescopes and detailed surveys, something more than a fully known object. It remains a system with a visible face and a hidden side, a structure that invites both measurement and imagination. And as the boundaries of what can be observed continue to shift outward, the presence of what cannot yet be seen becomes a quiet reminder that the story of our galactic home is still very much in progress. Somewhere along the path between looking up at a familiar night sky and learning about the vast layered structure that lies behind it, there is a subtle change in how place begins to feel. It is no longer just a point on a map or a coordinate in a model. It becomes a position within a story that is still being written, shaped by discoveries that continue to shift the background against which everything else is set. The Milky Way, once imagined as a simple spiral with a clear outline, now appears as something more like a deep, overlapping system of stars, gas, dust, dark matter, and motion, stretching farther and blending more gradually into its surroundings than earlier pictures suggested. Within that expanded view, the solar system does not move through a neatly defined home. It travels through a structure that is both familiar in its basic features and unfamiliar in its full extent. This shift in understanding changes the way inside is defined. When the galaxy was thought of as a disk with a modest halo, being inside it felt straightforward. You were either in the disk in the halo, or beyond the galaxy altogether. As the halo grows in scale and complexity, and as its boundaries become more diffuse, that clarity softens. The solar system sits well within the stellar disk, far from the most distant halo stars and far from the faint extended reaches of the dark matter envelope. But the influence of that envelope still shapes the path of the Sun and its planets, even if it cannot be seen directly. In this sense, being inside the Milky Way now means being part of a structure whose defining features extend far beyond what is visible, and whose true outline is drawn as much by gravity and history as by light. This expanded picture also reframes how the galaxy's center is understood. For a long time, the galactic center was a point of reference, a place from which distances and motions were measured. It was the anchor of the map. As more is learned about the bar-shaped structure in the inner regions, the distribution of stars around it, and the complex flows of gas that move through it, that anchor begins to look less like a fixed hub and more like a dynamic region in its own right. The solar system's relationship to this center is not just a matter of how far away it is a matter of how the entire galaxy's mass, including its unseen components, shapes the Sun's orbit and the broader gravitational environment. Understanding this relationship requires thinking about the galaxy as a whole, not just as a collection of bright features. There is also a temporal aspect to this sense of place. The Milky Way that exists now is not the same Milky Way that existed when the Sun formed more than 4.5 billion years ago. The galaxy has grown, merged and changed over that time. The solar system's birthplace was likely a region of the disk that had already been enriched by earlier generations of stars, but that region itself may have moved, warped, and shifted as the galaxy evolved. In this context, the idea of a fixed home address in the galaxy becomes less precise. The solar system's location is not just a point in space, it is a point along a path, part of a long journey through a changing structure. As the understanding of the Milky Way's scale expands, that journey appears to take place within a much larger and more varied environment than once assumed. There are regions of the halo that may have been entirely absent or very different when the Sun formed. There are streams of stars from past mergers that did not exist yet, because the mergers had not happened. There are satellite galaxies that have since been absorbed, contributing material and stars to the Milky Way's outskirts. All of this means that the galaxy the solar system moves through today is, in some ways, a more extended and more complex system than the one it began in. This historical dimension adds depth to the idea of inside. It suggests that being part of the Milky Way is not just a static condition, but a role in an evolving structure. The galaxy is not a container that holds the solar system in a fixed shape. It is a system that both shapes and is shaped by the movement of its parts. Another way this expanding understanding affects the sense of place is through comparison. When the Milky Way is seen alongside other galaxies, especially those at different stages of development, it becomes clear that its current form is just one point along a spectrum of possible structures. Some galaxies are compact and dense, others are extended and diffuse, some are actively forming stars, others are largely quiet. The Milky Way's newly appreciated scale and complexity place it within a category of large, mature spiral galaxies with rich merger histories and extended halos. This comparison can make the solar system's position feel both ordinary and specific. Ordinary because it resides in a galaxy that follows the same broad rules and processes as countless others. Specific because the details of the Milky Way's history, its particular pattern of mergers, and its current structure are unique. In that sense, our place is both a common type of location in the universe and a one-of-a-kind environment shaped by a particular cosmic past. There is also a shift in how boundaries are perceived. In everyday life, boundaries are clear. A room ends at a wall. A country ends at a border. A planet ends at an atmosphere. The Milky Way does not have such clean divisions. Its stellar populations thin out gradually. Its dark matter halo extends invisibly. Its gravitational influence overlaps with that of other galaxies. Being inside the galaxy, therefore, means being part of a region that fades into something larger, rather than ending abruptly. This has implications for how the universe is conceptualized. Instead of thinking in terms of separate, isolated objects, the picture becomes one of overlapping systems, each embedded in a larger context. The solar system is embedded in the Milky Way. The Milky Way is embedded in the local group. The local group is embedded in a filament of galaxies. That filament is part of a vast cosmic web. Each level does not end cleanly. It blends into the next. This layered embedding can change the emotional tone of how place is experienced. Rather than feeling like a small point in a set of nested boxes, it can feel like a point in a continuous structure that stretches outward in all directions. This perspective does not diminish the importance of local scales. The Earth, the solar system, and the immediate stellar neighborhood remain the environments that matter most for daily experience and for the conditions that allow life to exist. But it does place those local environments within a much broader and more connected framework. There is also an effect on how the future is imagined. As the Milky Way's structure and scale become clearer, so does its long-term trajectory. The eventual merger with Andromeda is not just a speculative event. It is a consequence of the gravitational landscape in which both galaxies exist. Understanding the size and mass of the Milky Way's halo and how it interacts with Andromeda's halo helps refine models of how that future merger will unfold. From the solar system's perspective, this means that inside the Milky Way is a temporary condition, in the sense that the galaxy itself will eventually become part of a larger system. The solar system will not leave the galaxy, but the galaxy will change around it, absorbing another large system and becoming something new. This long-term view adds another layer to the idea of place. It suggests that even the larger structures humans meaningfully talk about are not permanent. They evolve, combine, and transform. The Milky Way's expanding scale, therefore, is not just a matter of adding more stars or more dark matter to the map. It is a sign of a system that is still in the process of becoming something else. There is also a connection between this expanding understanding and the way knowledge itself is experienced. As observations grow more detailed, the Milky Way becomes less like a solved puzzle and more like an open field of study. Each new layer of structure revealed, whether it is a faint halo stream, a distant star cluster, or a refined model of the dark matter distribution, adds to the sense that the galaxy is deeper and more intricate than previously thought. This can create a kind of intellectual humility. The idea that even our own galaxy, the one we inhabit, is not fully mapped or fully understood, highlights the limits of human knowledge in a tangible way. At the same time, it emphasizes the capacity for that knowledge to grow. The expanding understanding of the Milky Way scale is the result of generations of observation, theory, and technological development. It is a reminder that the picture of the universe available to any one era is not final, but part of a longer process. This process also affects how the night sky is perceived. To the naked eye, the stars appear as a pattern of points on a dark background. The Milky Way appears as a soft, glowing band. With the added context of a deep, layered galaxy, those points and that band take on additional meaning. Each star becomes a marker of a much larger structure. Each dark patch hints at dust and gas. Each faint region suggests an extended halo or a distant stream. The sky becomes not just a visual scene, but a map of a complex system that extends far beyond what can be seen directly. This does not require constant awareness to be meaningful. It can sit quietly in the background, a layer of understanding that does not change what is seen, but changes what is known about what is seen. There is also a social dimension to this expanding understanding. The story of the Milky Way is not written by a single person or a single group. It is the product of a global scientific community spanning cultures, languages, and generations. As new data from instruments like James Webb becomes available, it is analyzed, debated, and interpreted by researchers around the world. This collective effort shapes the evolving picture of the galaxy. In that sense, our place inside an expanding understanding is not just a physical position in space. It is also a position within a human network of inquiry. The knowledge of the galaxy is something that is built, shared, and refined through collaboration. This adds another layer to the idea of belonging. The solar system belongs to the Milky Way in a physical sense. Humans belong to a global effort to understand that galaxy in an intellectual sense. Both forms of belonging are part of the same story, one that connects local experience to cosmic scale. Another way this expanding understanding influences perspective is through the idea of rarity and commonality. For a long time, it was unclear how typical a galaxy like the Milky Way was. As surveys of other galaxies have improved, it has become clear that large spiral galaxies with extended halos and complex merger histories are not unusual. They're a common outcome of cosmic evolution. This suggests that the environment in which the solar system exists is not a rare or exotic one, at least in broad terms. At the same time, the specific details of the Milky Way's history, the timing and nature of its mergers, the distribution of its dark matter, and the pattern of its star formation are unique. This combination of generality and specificity is part of what gives the sense of place its texture. The solar system exists in a galaxy that follows common rules, but that galaxy has a particular story. As that story becomes more detailed, the sense of place becomes more grounded in a narrative rather than just in a set of measurements. There is also an implication for how the search for life elsewhere is framed. Understanding the Milky Way's structure and scale helps define the range of environments in which planetary systems exist. Some regions of the galaxy are more crowded and energetic, others are quieter and more stable. The solar system's location in a relatively calm part of the disk appears to be one of many possible places where complex life might arise. As the map of the galaxy extends and becomes more detailed, it becomes possible to identify other regions that share similar characteristics. This does not mean that life is guaranteed elsewhere, but it provides a context for thinking about where conditions might be more or less favorable. In this way, the expanding understanding of the Milky Way's scale connects to some of the most enduring questions about humanity's place in the universe, not in the sense of providing direct answers, but in the sense of defining the stage on which those questions are asked. There is also a quiet aesthetic element to this broader picture. The idea of a galaxy that fades gradually into a larger structure, that is layered and connected rather than sharply bounded, can be seen as a kind of cosmic continuity. It suggests that the universe is not a collection of separate objects, but a network of systems that blend into one another. From that perspective, inside and outside become relative terms rather than absolute categories. The solar system is inside the Milky Way, but the Milky Way is inside the local group, and the local group is inside the cosmic web. Each level is both a container and a contained. This nested structure can be a useful way of thinking about scale without reducing it to a hierarchy of importance. Each level matters in its own context. The Earth matters for human life. The solar system matters for planetary dynamics. The Milky Way matters for the long-term environment of stars and planets. The cosmic web matters for the distribution of galaxies. All of these scales coexist, and none of them fully defines the others. As the understanding of the Milky Way continues to expand, it is likely that this layered sense of place will become more prominent. The galaxy will be seen less as a single object, with a clear outline, and more as a region within a continuum of matter and energy. This does not make it less meaningful. It makes it part of a broader, more connected picture. There is also a personal aspect to this. For someone learning about the galaxy's scale, there can be a moment of disorientation, a sense that familiar ideas about distance and size no longer quite fit. This is often followed by a kind of adjustment, where the new scale becomes part of how the universe is imagined. That process of adjustment is, in a way, a small version of the larger scientific process. Both involve taking in new information, letting it challenge existing models, and then integrating it into a more complex understanding. In the context of the Milky Way, this means moving from a simple picture of a spiral galaxy to a view of a layered, evolving system with fuzzy boundaries and deep history. Our place within that system becomes less like a point on a simple map, and more like a location within a story that stretches across space and time. As that story continues to unfold, there will likely be more revisions, more extensions, and more layers added to the picture. Each of these will subtly shift how the galaxy is understood, and, by extension, how the solar system's place within it is perceived. This ongoing process does not lead toward a final, fixed answer. It leads toward a deeper, more textured sense of connection, one that links local experience to a vast, evolving structure. And within that structure, the idea of our place becomes not just a matter of where we are, but of how we understand where we are, and how that understanding grows along with the map of the galaxy itself. Eventually, attention has a way of returning home, no matter how far it has wandered. After moving through ideas of halos, dark matter, distant stars, and structures stretching hundreds of thousands of light years, awareness drifts back towards something familiar. The room you are in, the quiet sounds around you, the steady presence of the Earth beneath everything else. The sky outside has not changed. The stars look the same as they did before any of this was known. The Milky Way still appears as a soft band of light, faint or brilliant depending on where you are and how dark the night happens to be. Nothing about the view itself announces that the galaxy is larger, deeper, and more complex than earlier generations imagined, and yet the meaning of that view is shifted. Knowing that the Milky Way extends far beyond what the eye can see does not alter the pattern of stars overhead, but it does change the scale of what that pattern represents. Each visible point becomes a marker, not of an isolated object, but of a vast structure that continues well past the limits of sight. This does not require effort to hold in mind. It can sit quietly, like background knowledge, influencing perspective without demanding attention. The Earth continues its familiar motions. It rotates once every 24 hours, carrying day into night and night into day. It orbits the Sun once a year, defining seasons and cycles that have shaped life for billions of years. The Moon circles steadily, pulling tides across oceans and subtly influencing the rhythms of the planet. All of this remains unchanged by the discovery that the galaxy is larger than once thought. The Milky Way does not press closer because its scale has been revised. The halo does not suddenly reach into daily life. Dark matter does not announce itself in any tangible way, and yet, the background context has expanded. The Earth is not just a planet orbiting a star in a spiral arm. It is a planet orbiting a star that moves through a layered, extended galactic structure, one that includes faint stars far beyond the bright disk, and an invisible mass that shapes everything else. This expanded context can feel abstract at first, but it has a way of settling into something more grounded. Consider the night sky as a ceiling rather than a destination. For most of human history, the sky was a boundary. It marked the limit of reach and understanding. The stars were fixed points, distant and unreachable, symbols rather than places. Modern astronomy removed that ceiling by revealing depth, motion, and scale. The stars became suns. The Milky Way became a galaxy. The universe became vast beyond easy comprehension. Now, with the realization that even our own galaxy is larger and more diffuse than previously believed, that ceiling lifts again, just slightly, revealing another layer of distance and connection. But the lifting is gentle. There is no need to chase the expansion of scale outward indefinitely. It is enough to acknowledge that the sky above is not a flat surface, but a window into a structure that extends far beyond what the eye can follow. From the surface of the Earth, that window is always partial. Light from distant stars has travelled for years, centuries, or tens of thousands of years to arrive. The faint glow of the Milky Way carries information from regions that existed long before modern humans ever looked up. This time delay creates a kind of quiet separation. What you see is not what is happening now. It is what happened long ago, arriving just now. That fact alone can create a sense of distance that is not physical, but temporal. And yet the Earth remains firmly anchored in the present. Gravity holds everything in place. The ground supports weight. Air fills lungs. Sound travels through space at familiar speeds. The body exists at a scale where light years and dark matter halos have no immediate influence. This contrast between the vastness of the galaxy and the immediacy of life on Earth is not a contradiction. It is a layering. The Milky Way provides context. The Earth provides experience. One does not replace the other. As the understanding of the galaxy expands, it becomes easier to see how small-scale and large-scale realities coexist without interfering. The Sun's orbit around the galaxy takes hundreds of millions of years. Earth's rotation takes hours. Human thought takes seconds. Each scale operates within its own rhythm. The discovery that the Milky Way's halo stretches farther than once believed does not speed up or slow down any of these rhythms. It simply adds another layer above them. In practical terms, nothing about daily life changes. Clocks keep time, calendars still work. The night sky looks familiar, but the mental map in which all of this takes place becomes slightly larger. The Earth is not centered in the galaxy. It is not near the edge either. It occupies a middle distance, orbiting quietly in a region that has been stable enough for complex life to develop and persist. This stability exists within a galaxy that is dynamic, layered, and still evolving. That combination is not accidental. Galaxies like the Milky Way, with extended halos and long histories of gradual growth, tend to provide environments where stars can orbit for billions of years without frequent disruption. Planets can remain in stable orbits. Life has time to experiment, adapt, and endure. In that sense, the Milky Way's true scale is not just a matter of size. It is part of the reason the solar system has been able to exist as it does. The galaxy's dark matter halo, invisible and silent, plays a role in maintaining this stability. Its mass helps hold the galaxy together, smoothing out motions and shaping orbits over immense spans of time. None of this is visible from Earth, but it is present nonetheless. There is something quietly reassuring about that. Much of what supports the structure of the galaxy does so without drawing attention. Much of what shapes the long-term environment of the solar system operates on timescales far beyond human concern. This allows life on Earth to unfold without needing to respond to constant cosmic upheaval. The galaxy is active, but it is not chaotic. It has structure, but not rigidity. It changes, but slowly. This balance is part of what makes it possible to look up at the sky and feel both small and secure at the same time. As understanding deepens, the sense of being under a bigger sky does not have to feel overwhelming. It can feel spacious instead. The idea that the Milky Way extends farther than once thought does not compress human experience into insignificance. It expands the setting in which that experience occurs. There is more room around everything, more depth behind what is seen, more history layered into each point of light. From the surface of the Earth, the sky remains a familiar dome, but mentally it becomes a cross-section of something much larger, a thin slice through a vast three-dimensional structure. That structure includes regions of the galaxy that are faint, ancient, and sparsely populated. It includes streams of stars from past mergers drifting slowly through the halo. It includes an invisible mass that outweighs everything visible. All of this exists whether or not it is being thought about, and that is part of what makes the knowledge restful rather than demanding. The galaxy does not require constant attention. It does not ask to be monitored or understood all at once. It is there, moving slowly, carrying the solar system along with it. When awareness returns fully to Earth, to the quiet of a room or the darkness outside a window, the expanded understanding of the Milky Way can remain in the background, like a deep foundation beneath familiar ground. Nothing needs to be done with it. There is no action required. It is enough to let the idea settle. The Earth is small relative to the galaxy. The galaxy is large relative to the Earth. Both facts can coexist without tension. From one perspective, the solar system is a minor component of an enormous structure. From another, it is the only place where life is known to exist. Perspective determines meaning. Neither scale cancels the other. As the mind moves between these scales, there is often a moment where the sense of urgency softens. Problems that feel large on a human scale do not vanish, but they take on a different proportion. Time feels slightly less compressed. Space feels slightly less crowded. The knowledge that the galaxy moves on timescales far longer than any individual life can create a sense of continuity that is calming rather than alienating. The Milky Way existed long before Earth formed. It will continue long after current civilizations are gone. That continuity provides a kind of cosmic background stability. Within that stability, individual lives unfold, brief but meaningful. This contrast does not diminish human experience, it frames it. There is also something grounding about realizing that Earth has always been under this larger sky, even when its scale was unknown. Ancient people looked up at the Milky Way without knowing it was a galaxy. Early astronomers mapped stars without knowing their distances. Entire cultures developed stories, calendars, and philosophies based on the same sky that exists now. The difference today is not the sky itself, but the depth of understanding behind it. That depth does not replace older ways of relating to the sky. It adds another layer. The Milky Way can still be a visual presence, a source of wonder, a quiet reminder of something beyond daily concerns. Now it is also understood as a vast structure, one whose edges fade gradually rather than ending abruptly. That fading edge is important. It means there is no sharp boundary where the galaxy stops and emptiness begins. There is a transition, a thinning, a gradual blending into a larger cosmic environment. In that sense, being under the Milky Way is not like being under a roof. It is more like being within a field that extends outward in all directions, becoming less dense but never entirely absent. This idea can be allowed to drift through the mind without needing resolution. It does not ask to be visualized perfectly. It does not demand precise numbers or diagrams. It can exist as a general sense of scale, a quiet awareness that the environment surrounding Earth is larger and deeper than it appears. That awareness does not need to be held tightly. Like the galaxy itself, it can be allowed to move slowly, to settle, to fade into the background when attention turns elsewhere. The Earth remains the place where gravity feels strong, where air has weight, where surfaces support bodies. The sky remains a place of light and darkness. The Milky Way remains a presence overhead, unchanged in appearance, expanded only in understanding. As attention continues to drift back toward the immediate world, there is no need to hold on to the vastness consciously. It can remain as context rather than content. The galaxy does not require awe at every moment. It does not require constant reflection. It simply exists, and within it, the Earth continues to turn, the night continues to arrive, and the sky continues to stretch overhead, quietly containing far more than it reveals. That is enough. Nothing needs to conclude. The Milky Way does not reach an ending point, and neither does the process of understanding it. The sky above remains open, extended, and patient,